Hey class, this is lesson 524, multiplying binomials that involve subtraction. I don't know if you've noticed it, but every set of binomials we multiplied so far has just had addition in it, so we're going to learn how to deal with subtraction. And remember, we used rectangular diagrams to help us understand why we're doing what we're doing. So check this out. If you start with a square, the area of that square is d squared. And now instead of adding to both sides of that, we're going to add to one side. You can see that here we added 3 units to that side. And then the other side we're actually going to take away. So if you look closely at this length here, the whole length is d. And this length from there to there is actually d minus 1. So the area we get when we multiply d minus 1 times the quantity d plus 3 is this area. And let's just think about how that works and how we can come up with our expanded expression using that diagram. So remember, this part right here is d squared. So I'm just going to put that down. And this part right here is 3 times d. So I'll add that on. Now we have to take away the 2 parts that are shaded. And this length right here, that strip is 1 wide, and d from there to there is d long. So that strip there is 1d that we have to take off. And then this other little strip on the end is 1 by 3. So we need to remove 3. And then we can simplify that and we get d squared. We can combine 3d and minus 1d, and that makes plus 2d minus 3. So just like when we were adding them, you end up with a trinomial. And there's usually 2 things you can combine in the final product. So we just kind of have to watch our signs when we're doing these. In this first set, we will expand the expression using the distributive property. So that means I'm going to take b minus 2, that whole expression, and multiply it by both b and 3. So we're going to multiply first by b, and then by 3. And then to simplify that, we will expand each of those expressions using the distributive property again. We get b squared minus 2b plus 3b minus 6. And then we can combine like terms. Minus 2b plus 3b makes 1b. And our final trinomial is b squared plus b minus 6. All right, I'll do one more with you like that, and you can do the other ones. So let's try this one here. We're going to multiply 2 plus e. Actually, just to try and avoid the having subtraction in our expression, let's multiply 3 minus e times both of the parts of that first binomial. So we're going to have 2 times the quantity 3 minus e plus e times the quantity 3 minus e. And then we get 2 times 3 is 6. 2 times e is 2e, but notice there's a minus in there, so we get a minus in our expanded expression. E times 3 is 3e, and e times e is e squared, but there's a minus, so it's minus e squared. And then we combine like terms. Minus 2e plus 3e is 1e. So 6 plus e minus e squared. All right, number 4 says a certain rectangle has an area y squared plus 5y minus 2y minus 10. Draw a rectangular diagram to represent this expression. So let's start with the square for our y squared. So that part is y squared. All right, and we're going to have to add on to that 5y, so I'm just going to tack on a little bit on the end here. On the y side, we'll add 5 here. All right. And that should have been y there. So now this space right here is 5 times y. Okay, now we need to subtract 2y. So on this part of the expression, I'm going to go back and cut off this much space, and that's 2. So now the top, you'll notice this part from here to right here is y minus 2. And so my expression is, so I'm talking about this red square, red rectangle right there. That's y minus 2 times the quantity y plus 5. And when I expand that expression, I get y squared plus 5y minus 2y minus 10. All right, so expanding expressions, binomial expressions with subtraction, you just have to watch the sign. This is a review here. If we multiply 4x times 3x, we get 12x squared. If we multiply 4x times 2, we get 8x, but there's a minus in there, so it's a minus 8x. And same thing here. Now, instead of just distributing 4x like we did in part A, we're going to distribute 3x minus 1. So we're going to do 3x minus 1 times 5x, and plus 3x minus 1 times 4. And so we get 3x times 5x is 15x squared, minus 1 times 5x is minus 5x, 3x times 4 is 12x, and minus 1 times 4 is minus 4. And then we can combine like terms and we get 15x squared plus 7x minus 4. All right, I'm going to do just a couple of these problems here, how we can use our multiplication of binomials to help us solve problems. There's a new definition you need to know here. It's a counterexample, and when you're trying to prove something, you either need to show that it always works, or you need to give what's called a counterexample, which means one example where it doesn't work. So, Tommy claims all odd numbers are divisible by 3. Is he right? If he is, explain why. If not, give a counterexample. Well, if Tommy picked a number like 3, that's an odd number. That certainly is divisible by 3. 3 divided by 3 is 1. That's a whole number, so it's divisible by 3. Let's try the next odd number, and that's 5. 5 divided by 3 is 1.6 repeating. And that, so we can see 5 is not divisible by 3. So Tommy's not right, and all we need to do to show he's not right is find one example that doesn't work, and that's called a counterexample. All right, Jordan has another claim here. She claims there is only one even prime number. Is she correct? Well, you need to remember what a prime number is. A prime number is any number with exactly 2 factors. So, like number 41 is prime because the only factors of 41 are 1 and 41. The number 7 is prime because the only factors of 7 are 1 and 7. So Jordan says there is only one even prime number. And I think she's thinking about the number 2. The only factors of 2 are 1 and 2. And let's just check a couple more, see if we can find a counterexample to that. See if we can find another even number that has only 2 factors. So the number 4, 1 goes into 4, 2 goes into 4, and 4 goes into 4. So that has, so that's not a prime number because there's 3 factors. The number 6 has 1, 2, 3, and 6. That has 4. The number 8 has 1, 2, 4, and 8. That has 4 factors, so that's not prime. And one thing you might have noticed on all these is it seems like 2 is a factor of every number that's even, which is true. So that's how we're going to explain why. We know that any number, let's say any number n, has at least 2 factors, 1 and itself. If n is even, then it has one more factor. And if it's greater than 2, then that's the number 2. So every even number has at least 3 factors, 1, 2, and itself. So I think she's right. Jordan's claim is true. All right, let's look at some other problems. Let's see, Olivia, she thinks she has found some number tricks. And we're going to either prove it or give a counterexample if it's not true. So number 9, Olivia says, take any 4 consecutive integers. Just a reminder what consecutive integers, they're like these, where each number is one more than the previous number. So these could be the 4 consecutive integers that she's talking about. So she says, take any 4, multiply the least number and the greatest number, then multiply the remaining 2 numbers. If you subtract the first product from the second, you will always get 2. Okay, so what she's saying is, if I multiply 56 and 52, and then if I multiply 53 times 54, that if I subtract those 2 numbers, I'm going to always get 2. So let's see if that's true. I hope you caught that little mistake there. This number should be 55. So Olivia is saying that if we take the least and the greatest, so 55 times 52, which equals 2,860. And then if we multiply the 2 remaining numbers, 53 times 54, which is equal to 2,862, that if I subtract the first product from the second, so if I subtract those 2, I'll always get 2. And in this case, I did. Now remember, to disprove something, all you have to do is find one counterexample. Let's pick some easier ones here, like maybe the numbers, I don't know, 3, 4, 5, and 6. So if I multiply 3 times 4, I get 18. If I multiply 4 times 5, I get 20. If I do 20 minus 18, I get 2. So it seems to work again. And if you want to pause and try a couple more, go ahead. But I think Olivia's onto something here. I think she's right. So the next step would be for us to prove that it's always going to work. And I'll show you how to do that. What we're going to do is let expressions represent the 4 consecutive numbers. So let's let the first one be x. Then the next one is one more than that. We can call that x plus 1. So that's the second one. The third consecutive number would be 2 more than the first, so x plus 2. And the fourth one would be 3 more than the first one, so x plus 3. And what she's saying is that this number times this number is 2 more than this number times that number. So let's see if she's right. So if I do x plus 1 times quantity x plus 3, I get x squared plus 1x plus 3x, that makes 4x, and then 1 times 3 is 3. If I multiply sorry about that, I multiplied the wrong one. If I multiply the middle 2, that's x plus 1 times quantity x plus 2. So that would be 1x plus 2x would be 3x here. And then 1 times 2 is 2. I get that. Now if I multiply this one and this one, I get x times quantity x plus 3, which is x squared plus 3x. And if you look close, x squared plus 3x is that part. And notice that this one is 2 more than that. So that proves that Olivia is right. All right, that's the end of the video. I'll see you tomorrow.